Thanks, sir, for a very modest introduction. And thanks to everyone present here for waiting for this last session. And I really thank the organizers for giving me this opportunity to speak. So as a last presenter, my job is to summarize, and that would be exactly what I would be doing with an additional tinge of how, as the earlier speaker mentioned, interdependency in this segment is very, very crucial, and it is more essential in today's scenario where independent activity cannot lead to a particular goal that we have all assembled here for. Interdependency of chemical, physical, and biological processes are highly essential to solve the problem at hand and to evolve into solutions that will work for us for the future. Right. I come from a research R&D lab, so the data that I'm going to present or what I'm going to talk of is of purely R&D nature, and we are looking for partners to take this up, to collaborate with us, and to initiate activity in this zone. So first and foremost, I draw your attention to this picture where our whole discussion for the last 2 days has focused on. Now here we are looking at a classical oil spill where there is a huge amount of oil on the top, and then there are small particles that are dispersed down to the bottom, and you have a huge variant of the top layer, which is water in oil, and the bottom layer, which is oil in water scenario. Now, these are two different scenarios that we have, and the kind of mechanisms that we need to clean this up are also going to be a little distinct from each other. Current strategies that we have involve a lot of physical treatment, we have chemical treatments, and we also have biological treatments. Like Professor Banwarilal, he explained to you how bioremediation is a very crucial factor, and it is a long-term activity that you do to clean up the soil. However, before we do bioremediation, there is a lot of activity that we need, both from the physical as well as the chemical side, so that the biological systems can take up and do their job. In the morning when I was preparing my slides, I was going through a couple of YouTube videos or TED Talks that were there. And there was this beautiful presentation by another lady scientist who said that Mother Earth is capable of handling everything. Any dirt that you give, the earth can process and reprocess it and convert it into a usable form. There is only one condition, that we don't want humans there. Because the greed that humans have destroy the entire ecological balance and distort things and do not allow Mother Earth to do its job. So microorganisms, or the bioremediation part, is basically Mother Earth's contribution into this entire scenario. We have specific microorganisms which can eat up hydrocarbons. As Sir was discussing, we have specific microorganisms which are sulfur-reducing bacteria. There are a huge repertoire of bacteria around us. Even in this room today, or even in individuals like us, we carry a repertoire of microorganisms which do cleaning jobs for us, which do digestive jobs for us, which produce enzymes so that we remain healthy. So everything is out there, but we need to process it. We need to chew our food before it enters into the gut. That is mechanical activity. There are acids in the stomach, which is chemical activity, and finally then the bacteria can do its job. So it is interdependency that activates here. The physical processes that we have, basically the different kinds of skimmers and the different methodologies that we can have here, are able to recover 95 to maybe 98% of oil that is present there. What happens to the last 2% or to the last 10% that is there? The dispersants come in. You add in dispersants, you reduce the size of the particle, and it just disappears into the environment. Now, where does it go? It lands up in the stomach of fish, it lands up in the stomach of marine organisms. And finally, it comes back to us. So is that a solution to the problem? There is a huge oil left over in this aspect also. So therefore, people look at options of burning it up, in situ burning and ex situ burning, both of it. But the problem is not ending here. You have air pollution. Finally, we come to bioremediation. You can do intrinsic bioremediation, we can do engineered in situ bioremediation. There are a whole lot of different methodologies of doing bioremediation. Biospersing, bioventing, sparging, stimulating, bioaugmentation, natural attenuation. All these are ways and means by which we are actually allowing the entire microbial community to thrive. But the problem here is you are giving, maybe like Professor Banwari Lal was discussing, we have to offload tons and tons of bacteria onto the soil to actually start the activity. So it is that you are actually making a biocatalyst in kilos of quantity and putting it out there for activating. If you're relying on nature, you are actually asking a group or a handful of bacteria or yeast strains to grow rapidly on the hydrocarbon that is there and then do its conversion jobs. There are limitations to this entire system. There are limitations because the organisms need to adapt, then they need to identify the hydrocarbon as food, and finally, once they identify the hydrocarbon as food, then they start to eat it up, and they eat it up pretty efficiently. But that period, do we have that time? Because by the time the organism realizes that it is supposed to eat it, we have lost almost a month, and we are sitting on the oil, and we have no solution to the problem. And that's when we look at solutions which are combinatorial methods, where chemical, biological, and physical methods can be coupled together. Now, in this scenario, first and foremost, I present to you natural sorbents in the form of insoluble materials that can be used for capture. These are there in principle and are being used. The point that I was trying to make here, the point that I'm trying to make here is that the rate of sorption, the rate of adsorption, the oil retention on the biopolymer, and the ease of application all have a relevant significance in this entire scenario. Very recently, I was looking at a German scientist who has come up with this entire concept of hair being used as an adsorbent. The thought process was, when we have marine birds, the oil sticks onto their feathers. So essentially, hair is going to be an adsorbent. And because his justification to the entire thing was hair is a natural polymer, it gets degraded. But do we have the quantity or the volume of hair for such a kind of application is the question that we have, right? Then you have cellulose, activated graphite, bio-based aerogels, lignocellulosic materials which come in here. My interest in this area is more because I have worked most of my career in lignocellulosic materials. And from there, cellulose, lignin, these look to be a very promising solution to this problem. We are also extensively looking at coagulation and flocculation. This is essential, or this becomes an application when we are looking at a scenario of oil in water. The oil particles are very small, they may be emulsified, they may be dispersed, and they are difficult to capture onto any system. In this scenario, if we have flocculants and coagulants which can entrap the oil and localize them in flocks, it becomes a better scenario for the bacteria to act on. Coming back to the adsorbent or the absorbent category, we look at a huge variety of lignocellulosic waste that is there, extract out the cellulose, and try to use this cellulose as the bioadsorbent for the entire oil content. Now, this adsorbent can then be further used up for multiple applications. We are also looking, my lab is also looking at lignin, which can again accumulate the oil and function as herders, and this can then be used efficiently for either as equivalent to coal because it has a similar calorific value, or it can be used for multiple other applications. So this is where I come from, my group which works on renewable carbon engineering, where we look at different waste streams and try and capture the waste streams and put them together in a sustainable manner for the different feed applications. I came to this conference because we were working very closely with Infinitia Biotech, and they had a preparation of bio-based enzyme and microbe combination which was to be used as a bioremediation agent. We did trials onto their agent, and we used our integrated or interdependent system where we first physically separated the bulk of the oil, and then secondly used a coagulation agent to trap the residual oil, and finally the biodegradative agent which could convert the oil completely. And the time and efficacy of the whole preparation, within 15 days we were able to reduce the ppm levels to 211. It is still far from what we would want to reach, but the overall removal of the contaminated water that we could effect was around 99%. So that's all from me. Thanks, and thanks for listening.
Thank you very much, Dr. Annamma. Very nice presentation, bringing together mechanical engineering, chemical engineering, and bioengineering. And the combination should really work the way you are presenting it, and because we know, after 2 days of session, we know that ultimately it is said that you can't have oil without oil spill. And even if you don't produce oil, natural seepages are there. And natural seepages are since ages. If they were there, as you said, Mother Earth takes care of everything, they were taking care of that thing also. There was a natural degradation. Now we are using the technology to aggravate that processes, and we are using here to combat this oil spill. And as we all see, hardly 70% oil is spilled oil is taken care by the natural degradation. So thank you very much, Dr. Annamma. Now I open the house for any question to Dr. Annamma. You may please take your seat and answer from here.
Thank you. Thanks, everyone.
Oil Spill India 2022 is dedicated to the Honorable Prime Minister's Swachh Bharat Abhiyan and Clean Seas.